Hello, everybody. My name is Brian Hudson from ABB. I'd like to welcome you to today's Protective Relay School webinar. This is just one in a series of topics being presented by ABB. The goal of today's presentation is to provide you with an introduction to IEC 61850. The presenter today is Alejandro Sznakowski. And I do want to let you know that we anticipate that this presentation will last about an hour to an hour and 15 minutes. Because of the very large number of attendees, we will not be able to take your questions verbally, but I would welcome you to type your question into the question pane in your control panel. And we have people standing by to either respond to you in writing or to through a text message, or in some cases Alejandro will read your question on the air and respond to it. Again, because of the very large number of attendees, we will do our best to get to as many questions as we possibly can, but it is possible we may not be able to answer them all. Alejandro graduated from Florida International University in Miami with a BS in electrical engineering. He's conducted research in the field of digital relays and centralization of protection functions within a substation. In 2002, he worked for Boussier Communications, where he engineered, deployed, and tested Ethernet networks. In 2005, joined ABB, where he's been in a variety of roles from application engineering to management. He is currently residing with his family in Raleigh, North Carolina, and is the manager of application and support for substation automation products in North America. And again, I welcome you to today's conference. Just to let you know that this session is being recorded. So if for some reason you have to drop off, or if you know of someone who was not able to attend the live event, you are welcome to come back and view the recording, or to direct anyone else there. With that, I'll turn this over to Alejandro.
Thank you, Brian. Good afternoon, everybody. So for the next 60 to 90 minutes, though, we'll be diving into IEC 61850. And these, in a nutshell, though, these are really the 5 points that I would like to cover today. Number one, just a brief history of IEC 61850. Then we'll jump into IEC 61850 as a standard model, the standard data model, and SCL, which stands for Substation Configuration Language. And then we'll talk about the three, I'll call them the three very distinct technologies, though, or communication protocols that are within IEC 61850. Client server, which is an MMS-based protocol that allows IEDs to provide information or report information, status points, and so on, to centralized locations such as a gateway, remote terminal unit, so on. We'll touch base and learn a little bit about goose messages, okay? And we'll do the same with sample measure values. So with that in mind, though, these are the 5 topics, though, that we'll cover. As Brian mentioned, questions are welcome through the questions pane in your GoToWebinar interface, and we will be addressing them as they come. So let's get started. So IEC 61850 and its origins, though. So when looking at IEC 61850, it's really the convergence, though, of 2 different initiatives, though, that were ongoing during mid-1990s, though, around the world. And in essence, what we had were two different initiatives, though. One which was being run in North America, though, by the UCA, which stands for Utility Communications Architecture Group. And then in the IEC world, we also had working groups, though, inside Technical Committee 57, though, which we're venturing, though, or exploring the need for a standard communication protocol, though, for substation automation applications. So when looking at the UCA group, we could see that we were back in 1994. This started though as an EPRI initiative, okay, and then right around 1996, with AEP though here in the U.S. This is one of the major drivers though from the utility sector though. We're really pushing though to identify an Ethernet-based protocol though that will allow data sharing similar to Modbus DNP or other station-type protocols though that were in use at the time, but also the need for high-speed exchange of binary signals among IEDs. Okay. One of the interesting initiatives though from this specification though again was perhaps the need of the specification of utilizing the communications network to replace control wiring. So this is something that's important to take into consideration when we talk about the discussion regarding goose messages though, where this is pretty much the urging though, and we will see as we look at some of the settings though that are related, or some of the parameters though that need to be taken into consideration to consider a goose message though, how that comes into play. When looking at IEC 61, when looking at the IEC track, it was right around 1995 when IEC Technical Committee 57 began the standardization effort though to define the next generation of local area network-based substation automation and control. So as I said, you essentially had two different initiatives ongoing, one from UCA and one from the IEC world. And it was in 1997 when these two groups of people though came together, met, and it was decided to have one single approach to resolving this problem though, or developing though this initiative of having a single open source substation automation protocol for substation automation. So when looking at this, again, just a picture though that perhaps crystallizes though that comes at a little bit more. We had the UCA from the NC world, and then from the IEC world, we had 6150 though, which really came from 608-7103 to really, to really kickstart the efforts of IEC 61850 as an international standard. And when looking at the role, and something that's worth mentioning though, when looking at the role of UCA, it's very important though. UCA continues to this day to provide significant interface though between manufacturers, consultants, and end users, and Technical Committee 57 that's in support of resolving issues, as well as creating application guidelines though for this new protocol. And from the standardization perspective, IEC 61850 really it's hosted by IEC Technical Committee 57 though we're voting and resolution though the standard actually occurs though. So when we talk about it being an international standard, it truly is, since again it's really the merger though of these two initiatives though, which since the beginning though both the UCA, the driving objectives for the UCA initiatives, as well as the driving objectives though for the IEC initiative though were actually quite common. When looking at this timeline though, it's pretty important though to highlight where ABB has been part of this effort though. And from 1994 to 2003, there's been a significant amount of effort, though, that our factories in Europe as well as here in the U.S. have been constantly involved in the standardization and working group efforts, though, to define and shape what IEC 61850 should be. From a development perspective, though, and testing, significant amount of interoperability tests have occurred among us and other vendors, though, of this particular project, though. And in 2004, that's when we actually had our first release, though, of IEC 61850 as a protocol implementation. In 2005, the UCA Users Group certified ABV's System Verification Center, where right now we are the only manufacturer, though, that has a System Verification Center to validate protocol implementations, though, in IEDs, though, and its systems themselves. In 2008, ABV had its first IEC 61859-2 process bus installation. In 2010, we released first UCA certified 61859-2 merging unit in the world. And as of this year, globally, we have successfully delivered more than 1,200 substation automation systems based on IEC 61850. Now, that's really just a brief story in regards to the standardization efforts, though, and process, though, that we went through to get to what we have today, which is this standard, though. Now, the question is, why 61850? Why is this something that's important, is relevant, though, and that's really being offered as a new solution, though, for substation automation communications? And what I would like to do here over the next 3 slides, it's show the architectures, though, for SA that we've seen over the years, though, and building up to, and what I'm doing is building up to then a comparison between what Modbus and DNP offer as SA protocols, though, and the gaps that 61850 feel, so that we have an understanding again as to why we have this this standard. So what we have here in this particular slide is a typical architecture of an RTU/hardwire substation automation system. So what you will see is we essentially have a set of panels for our protection and control equipment, or our protection relays. And then there's a set of panels and hardwiring, though, going into our remote terminal unit. So this architecture, the goal of this is provide information to operators, though, system operators, though, of getting an understanding, though, what is the topology of the substation. What are the loads in a particular feeder, though? What's the level of the voltage? What's the power consumption? These are all variables, though, that are of interest, though, and that are needed, though, to make operational decisions, though, in regards to the power system. So with a hardwire/RTU architecture, what we have is remote terminal unit cabinets that have binary as well as analog signals hardwired coming into this RTU. There's a significant amount of engineering that goes on taking this binary status point as well as analog points, which from the RTU perspective, they're just signals or status points, and then mapping those signals over to the application or their actual meaning, whether it's current for bay 1 in a particular, or for breaker 1 in a particular system, or bus A voltage. and so on. The key here, and one of the things that's described though on SA systems overall though is the saving of wires though, is that when you look at this particular architecture, there's a significant amount of hard wiring that goes from the primary apparatus over to the RTU cabinets, and also some of that wiring though it's also replicated though to go from the apparatus over to the protection and control relays. One example is, for example, the position of the breaker, 52A and 52B contacts. There's hardwired signals from the A and B auxiliary contacts of a particular breaker over to the RTU, so that the RTU can report up to SCADA what is the position of that particular breaker. In turn, there's also wiring that goes from those same A and B contacts over to a protection relay, which needs that information, for example, to get an understanding of whether the breaker is open or closed, to execute reclosing sequence though on a particular breaker. So this is again one example of where we have this replication of wiring. We move on, and with the introduction of microprocessor technology in protection relays, we now have an architecture where perhaps significant amount of the signals are now not hardwired over to a remote terminal unit, but in turn, since those signals were already wired over to the protection relays, again, thanks to communications protocols and thanks to microprocessor technology, we can use our protection relays, which have already existing wiring over to the primary apparatus, and via any type of protocol, communications protocol, have the relay report that information over to a data repository or a substation gateway. So from an application perspective, though, the flow of information is still the same. We want to have an understanding of what is the status of the equipment inside of the substation. With the first slide, there was replication of wiring between apparatus and relays, apparatus and RTU. Here we're essentially eliminating the hard wiring over to the RTU. We're utilizing the existing wiring from the apparatus over to the relay, and then we're using communications protocols to report those variables or those status points that are being monitored by the relay, and we're reporting them over to substation gateway though. So there's some savings though in regards to wiring though at that point. You're going to hear, or it's often said though when we talk about 61850 though, how we eliminate how 61850 is an open protocol though. And then in the next few slides though, I'll show when we talk about proprietary solutions though versus 61850, what do we mean exactly like that by that? Because on the next slide, the architecture, it's not so different though. So now when we move to what's envisioned though by IEC 61850 though, we have a couple of changes. Number one, instead of utilizing proprietary protocols though, or proprietary protocols, we're using IEC 61858-1 so that protection relays or IEDs can share their status points over to a data concentrator. And then the second component of this architecture, though, that's different from the prior slide, is that now we have the process bus. And what the process bus essentially is the wiring that we have in this slide between current transformers and voltage transformers, which is hard copper wiring, though, onto the relays. It's now replaced by fiber optic connections, though, that essentially carry both the current and the voltage information for the IEDs to perform their desired function, whether it's monitoring or protection, though. So based on those three pictures, though, let's now take a look and understand, though, what are the goals, though, of IEC 61850 as a standard, though. First one is interoperability, which is the exchange of information between IEDs, though, from several manufacturers, though. And although protocols such as Modbus and DNP offer the capability to exchange information, though, there's some intricacies, though, that are not defined, though, where integration comes into play, and we'll see that in a few slides into the presentation, though. Free configuration. What this means is the free allocation of function to devices, though. And what this means is, if, for example, though, I have a particular bay, though, where several IEDs are associated with that particular bay, it would be desired, though, to select which device, though, has the capability of providing the current information, or which device provides the voltage information, though, and how that all is documented, though, within the context of the substation. And then the other goal of the standard was this long-term stability. Have the standard be future-proof, follow progress in mainstream communication, as well as follow evolving system requirements needed by customers, though. And one of the ways that IEC 61850 addresses this, and you'll see, is that there's several components, though, to the standard. There's not a single document. Actually, it is written in multiple parts. And the idea is that by having these different layers or just different components, if for whatever reason the communications technology changes, there's no need to change or relaunch the whole standard. There's just going to be subcomponents, though, that will be modified and adapted. And that's the part where future-proof and or long-term stability comes from. Any questions? So as I just described, though, some of the technologies, though, that are part of IEC 61850. One of the things that it defines is the utilization of fast Ethernet, though. Okay, for the exchange of information between IEDs, either 100 Mbps or 1 gigabit per second, though. The introduction of the station bus, though. Horizontal exchange of information, high-speed horizontal exchange of information between relays, though, as well as reporting of information over to a gateway device. The process bus, though, which I just described, though, the introduction of sample measure values so that IEDs can execute their monitoring as well as protection functions of analog signals, though, that are digitized. Standard data model, though, IEC 61850 offers a complete modeling of both functions and apparatus and the allocation of those functions and apparatus within the substation, though. And all that, in turn, is documented inside the substation configuration language. Looking real quick, though, at the structure of the standard, though. There's 10 parts to it, though, and there are some parts of the standard that have subcomponents to it. And I'm here, I've listed, I've listed here most of them. But essentially, part 1 of the standard, it's an introduction and an overview. Part 2, it's a glossary. Part 3 discusses general requirements. Part 4 talks about the system and project management of that particular system, information flow management of the information about the substation automation systems project. Part 5 talks about the communication requirements for functions and device models. This discusses performance requirements, though, for some of the functions, though. How fast should a goose message be? Transmission times, transmission delays, and so on. There's a discussion about Ethernet network topologies, though, that should be considered for these types of systems, though. Part 6, it's essentially the introduction of the substation configuration language. Substation configuration language being an XML-based language that's utilized to document and perform the 61850 engineering. And then we have part 7, which really dives into the data model and how we are going to model information within the substation, though. So in a nutshell, though, parts 1, 2, 3, and 4 really discuss the introduction of the logical node concept, as well as the pieces of information that are part of each one of those logical nodes, as well as the format of those pieces of information. Part 8-1 talks about now really talks about communications protocols, though, and the mapping of those logical nodes over to existing communication standards, though. And when we refer to 6150A-1, we're really referring to two different, we could call them protocols, though. One, which is client-server, which it's utilized to exchange information from IEDs over to gateway or data repositories, though. And then also the horizontal, and the second one, though, being the horizontal exchange of binary information. Okay, and actually we have a question right here, so give me just 1 second so that I can read it. Okay, so one question that we just received, IEC 6150, can it be used with all IEDs? The answer is yes, as long as the IEDs or the relays or the pieces of equipment that are going to be part of the network, though, as long as they support IEC 6150 as a communications protocol, then the answer to your question is and most major vendors of at least protection and control relays, though, do support this particular standard. Going back to my presentation, though, then we have 6150 9-1 and 9-2, which they essentially define the protocol, though, the mapping of sample measure values or the process bus, which again is how do we take analog signals, though, from current and voltage transformers and transfer them in a synchronous manner, though, over an Ethernet network so that information can be utilized to execute monitoring as well as protection functions, though. So here we're talking about eliminating conventional CTs and PT copper wiring, though, and replacing that with a pair of fibers, though, that essentially will carry those same signals in the digital Ethernet packet. And then last but not least, we have a very important component of IEC 6150, which makes it a complete suite, which is the conformance testing. So when looking at this model, we're essentially covering 3 key aspects, though. Four key aspects, though. We're covering the specification or the performance requirements as to how the system should behave, as well as some suggestions, though, architecture-wise, as to how to implement the system. Number 2, 6150 is defining a data model, though, under which we could represent functions and pieces of equipment inside of the substation. Number 3, we're defining communication protocols, though, to exchange this information, which, as I mentioned, you really have 3: client-server, goes, and sample measure values. And then number 4, there is a framework defined for the testing and the validation of such systems. So when looking at Modbus or DNP or other protocols, though, most of those, though, definitely fall short, though, on those 4 categories, and these are the gaps, though, that IEC 6150 it's filling. And this slide right here, it just again talks about how we have this particular, we have parts 7.4 and 7.3 deal with the information models or the data model. Part 7-2 talks about information exchange, okay? And then parts 8-1 and 9-2 talk about the mapping to the particular protocols, though. So by having the standard written in layers, though, what this allows us to do is parts 7-4 and 7-3, which is the information model, it's something that's not too dynamic. And the reason for that is because, I mean, the pieces of equipment and the functions that are performed inside of a substation have not really changed that much, though, since the introduction, have not really changed that much over the years. I mean, you have a breaker, you have a line, you have a transformer, you have current transformers, you have voltage transformers, you have distance functions, you have overcurrent functions. So this part of the standard talks about how are we going to model that, okay? And what is the type of information that's of interest status-wise as part of those pieces of equipment or functions. So if we look at a protection function, though, trip or pickup targets, though, or some information related to settings would, of course, be of interest. These are the things that Part 7-4 and 7-3 deal with. Part 7-2, it's much more abstract, though, and actually deals with the mapping of that information over to and defining, though, how the exchange of information occurs. And then parts 8-1 and 9-2 actually deal with the mapping of that information or those data models over to communications protocols. And that's the part where, let's say that, you know, today we're using Ethernet, tomorrow we may be using some other type of technology. That's no problem. Perhaps there's no impact to Part 7-4 and 7-3, which deal with the information models, but that allows us to replace just parts of the standards, though, and not just have a situation where we have to revamp the whole standard or make, you know, components of the standard obsolete, though. In this particular case, though, everything is done over Ethernet/TCP/IP networks, so in its current shape and form. So let's talk about now. Let's jump into what I believe, though, it's really the key, you know, the key component of IEC 61850. Just gonna move this a little bit. I think we have another question here. Lack of required elements in the IEC is the primary reason for the lack of interoperability. Okay, so we have a question here. Please comment on the lack of required elements within the IEC 61850 standard. I see this as the primary reason for the lack of inter-vendor operability. I guess what I could say is this, and I think I can only assume that what we're referring to is when we look at logical nodes and the information that's available within a logical nodes, there's something that's called data objects and data attributes, which is essentially pieces of information that are associated with that particular logical node. Some of those are mandatory. Some of those are optional. You may have a condition where one particular IED, all IEDs, if they support a particular logical node, have to support all the mandatory elements inside that logical node. However, the ones that are optional are optional. When we talk about interoperability, though, of course, given that definition, you may have a condition where one device provides support for a particular piece of information that's optional, whereas the other device does not. But that's where, I mean, there's also within the context of the standard, though, there's specifications, though, that describe the capability of the devices, though, at which point that is something that, of course, becomes pretty important to review, though, as part of any 61850 substation automation system specification. Okay, And then we have another question here that says, what is IEC 61859-2 LE introduced by ABB? So as I said, IEC 61850, and there's actually, I have some slides of that later on in the presentation, though. But this is actually not something that's exclusively introduced by ABB. There's other manufacturers that support this. What we have right now from a process bus perspective, though, we have 9-1, which is the transmission of sample measure values as a point-to-point transmission through a serial link. And then we have 61859-2, which is the transmission of sample measure values via Ethernet networks, pretty much. When edition 1 of the standard was released, there were a lot of elements, though, that were not defined in the standard, such as sampling rates, number of data streams, or number of voltage signals, or number of current signals per data stream, and so on. So these were things that once the 61859-2 was published, it really left a lot of details, though, open to interpretation, which made it very hard for manufacturers, though, to come out with a design, though, that would guarantee that whatever we were working on would match what other manufacturers were working on. That became quite evident, though, and this is actually an issue that UCA took a leadership role on, and they released what's called 61850 implementation guide, which in turn is being referred to as 61859-2 LE. And what it is it's an application, it's an implementation guideline for 61859-2, which specifies sampling rate for protection functions, specifies sampling rate for monitoring functions, specifies the configuration of voltages and currents per data streams, specifies accuracies of time synchronization requirements, and so on. So it is not a new standard per se. It is based on the released and published 61859-2, but it's an implementation guideline that fills some of the ambiguities that were left open with the release of the current standard. So that's what it is. Okay. So going back to the data model, though, I mean, the core of 61850, okay, it's the standard representation of functions and equipment, its attributes, and its location within a system. So we're not looking at, a current signal in the context of a relay or a current signal in the context of a particular breaker. We're looking at a particular current signal or a metering function, though, within the context of the substation, though. And I'll just explain a little bit, though, in the next few slides as to why this is important. But hold that thought. This is really, really key. Okay. So to do that, I'm going to go ahead and do just a quick, to get an understanding as to why the standard representation of functions, equipment, its attributes, and its location within a particular system, why is that important? So let's take a look at Modbus and DNP. So when we look at Modbus or DNP as communication protocols, and by the way, this also applies to SPA, which is an ABB proprietary protocol, on other, any 10 bytes income. There's many other protocols, though, where this same definition, though, they will fall under this same, description that I'm about to provide. So these are communication protocols that essentially define data type, binary, analog information, counters, and they define a reporting structure so that these variables can be transported or can be shared from one piece of equipment over to the other. from one piece of equipment over to another piece of equipment, so that it's in a centralized, location, so that it can be used as part of a decision support system. From a Modbus perspective, though, and these are not all of the data types that Modbus defines, but just some of them. You have, for example, coils. You have input holding registers. In the case of coils, they're mainly implemented as just binary data, as seen, now just referring to protection relays. So it's mainly applied as a holding or as a repository for binary information. Then we have input and holding registers, which they can really be used to hold binary information as well as analog information. When you look at the Modbus implementation protocol, though, there's really no definition as to what a coil should be, what an input register should be, or what a holding register should be. And over the years, it was really up to the manufacturers to do a mapping or an association between the variables that were of interest to customers and those data points inside of inside the protocol map. In Modbus, though, you're looking at a polling reporting structure, so you actually have a master-slave interaction where the master asks a question to the slave responds with an answer. But again, the key here is it defines a reporting structure, it defines analog and an association between the data that a particular IED is monitoring and that particular data type. So when we look at this picture right here, let's call this breaker 1. We have breaker 1 phase a current. From a Modbus perspective, this would be a 4X holding register number 245. With that actually creates more questions. Well, is this a signed number or an unsigned number? Okay. Is this a 12, 16, or 32-bit analog value? Is the value being reported in primary or secondary? So from this perspective, though, you would probably need to go to a PDF file, to instruction book, or some sort of reference documentation that will provide you with some answers, though, in regards to this. And if you have different pieces of equipment from different manufacturers, though, you're probably going to have to do the same through each one of those. So again, key issue here that I'm pointing out is there's no relationship between the protocol information and the application, and there's no definition in regards to the format of the data that's being transported. And all of this information, it's important because ultimately this is going somewhere. This is going to go to a gateway. The gateway needs to be configured and needs to have all of these parameters, though, so that it can do its job. Now let's look at DNP. So what DNP does, though, it actually defines what's called objects. And again, just defining it broadly, you're looking at data types, binary, analog, counters, and so on. And then there's variants associated with each one of those objects. So here we expand out and we at least define variants where when we talk about analog values, there's definitions for 32-bit, there's definition for 16-bit, sign, unsigned, and so on. There's indexes for each one of these objects. And again, you actually have in this, when compared to Modbus, we do have a step forward where you now have both a polling as well as an unsolicited reporting type reporting structure. By unsolicited reporting, I mean that a particular IED will report the information back over to the gateway upon a change of state without having to receive a request. And this makes essentially better use of the bandwidth of the communications network, so that we don't have to have the master asking for the information. It essentially is just waiting for all the slave devices to send the information once something changes state. But again, there is no connection between the data, application, object, or location within the substation. So I'm still just looking at an index, I'm still looking at a register, I'm still looking at a memory address that within the framework of the protocol, there's no connection between that piece of information and the application. So in DNP, the same phase A current would look like this. Will look like object 30, which is an analog value, index number 5, for example. Okay, and then we still need to figure out what type of variant this is, and we still need to figure out how is the manufacturer how did the manufacturer define that particular analog quantity? Did it define it as a primary value, or when looking at some of those issues, though, integration essentially involves gathering all information from the IEDs, okay, having understanding of media or protocol converters that may be needed, though, if in the case that you have devices that do not talk a particular protocol, though, then you will need to perform protocol conversion. As part of integration requires a thorough understanding of the memory pointer register map of each one of the devices that you want to integrate into the system. So it's not just about the list of points that are available, but it's also the format of each one of those points, though, and the behavior of each one of those points, which will vary from manufacturer to manufacturer. And then once we have this, it's about programming your data concentrator to accept such information. So again, data types and data formats, so, and reporting structure are things that need to be defined as part of this. And as you could see in both Modbus and DNP, although we're defining data types and we're defining mechanisms to report the information, we're not being too specific as to what is the configuration of the information and what is the association with that information and the application. Those are things that are left open for the manufacturers to implement. And this is the part where this is the challenge of integration. If you're integrating devices, all the same devices from the same manufacturer, you can argue that you learn one device and then all the other ones will behave in the same way. However, as it is often the case, SA project, though, involves more than one kind of device, at which point requires, again, good amount of understanding, though, of all of these different things. So the question now is, once we now have this based understanding of what are the challenges, where does 61850 help? What is different about 61850 that helps us solve some of these challenges? And essentially, here's what we have as part of 61850, though, that helps us, that essentially helps us with some of these challenges. On the left, I actually have a column of functions and equipment, and we could see that, for example, position of breaker 1, and I have in this red square, though, what I'm calling breaker 1 right now within the context of the substation. I have device address number 5, binary input 4 in DNP for 52B, device address number 5, binary input 5. You could do the same for breaker 1, currents, okay? And you could see that now we have same device, but analog input number 10, 11, and 12 are our phase A, B, and C currents. And then for breaker 1, the status 51P and 50P targets, we're looking at binary input 6 and binary input 7. Now, let's take a look at how that information, or what is the addressing scheme of 61850. Well, in 61850, there's no binary input, there's no analog inputs, there's no counters. The information is presented within the context of the application. So if we're going to talk about the position of the breaker, we're not going to talk about a binary point. We're not going to talk about a digital point. We're going to talk about the position of the breaker. And there's something here that is defined within the standard, which is an XCBR, okay, which is what we call the logical node. And what the logical node is the representation of a piece of equipment or a function that's performed inside of the substation. And then for that particular piece of equipment or function, there are data attributes or pieces of information that are related to that particular apparatus, equipment, or function. So what are as part of XCBR or our breaker, we have something that's called POS or position, which is, as you guessed it, it's the position of the breaker. So as you could see, although XCBR right now does not ring a bell, as you learn the naming convention, though, at least the .POS, it's quite intuitive, though, that's referring to the position. Then let's take a look at our current measurements, where for our measurements, there's a logical node or a function called MMXU. And then as part of MMXU, you have an attribute that's called A for amperes. And then MMXU.A.phase A refers to the ampere measurements of phase A. MMXU.A.phase B refers to the ampere measurements of phase B, and the same for phase C. Now, let's take a look at our protection function targets. Well, again, we don't have binary information. We have a function that's called PTOC for protection time over current, and then there's a data object called operation or .OP. For our instantaneous over current function, we have PIOC, which is protection instantaneous over current. And we have a couple of questions here, so would like to go ahead and address them. So one question is, would you clarify station bus and process bus in the picture? I'm going to go ahead and take you all back here. That's not a good picture. Actually, I'm going to go forward real quick. Okay, so when we talk about we talk about the station bus. The station bus includes two components. It includes the exchange of information between IEDs. So if one relay, let's take for example a breaker fail scheme. Breaker fail scheme involves the exchange of information from a device that just operated a protection function and another device that's going to start a timer, for which it will wait, pick a timer for which it will wait to see whether the fault is clear or not. If the fault is not clear or the input signal to that particular device it's not quenched within a certain amount of time, another sequence of events will be started. That is rapid exchange of information between IEDs inside of the control house. Another component of the station bus, okay, is the exchange of information from each IED over to a gateway or a data concentrator inside of the substation. So it is referred to as the station bus because this is a network that's usually within, within the substation or within the control house building. Okay. When we talk about the process bus, we're actually talking about a network that is out in the switch yard, where inside each breaker, there's inside of each breaker though, or at the switch yard, you're going to have you're going to have current transformers as well as voltage transformers. Those current transformers and voltage transformers will be wired onto what's called a MU or a merging unit. And the merging unit, it's going to sample those analog signals from one side. And then on the other side, at its interface to the Ethernet network, it's going to generate a sample measure value data stream, which essentially is those analog signals now digitized in the form of Ethernet packets based on 61 and 59-2. Okay, that information is in turn published on the process bus network, though, which again, it's really referred to as this network, though, that's close to the apparatus or the primary equipment, though. There's also not, I mean, it's also envisioned, though, then within this context or within the process bus, you're also going to have binary signals, though, to, let's say, trip the breaker, though, if the breaker had the intelligence of receiving a goose message, though, to trip or to close. So it's not, you know, when we talk about process bus, we're not exclusively talking about analog signals. We're just referring to the network, though, that again, it's close to the primary apparatus, though. So when we look at this picture, though, here in this part, you know, we have the substation with the gateway, the HMI, and the relays. Okay. Here we have the bay cubicle, though, inside of the substation. And then here inside of the switchgear, though, you're going to have a network or your process bus network, though, that it's gathering, though, or making the connection, though, of those sample measure values. Then we have a question here that what are ABB's offerings for process bus solution today? Are they available in a product catalog? Right now, from ABB Substation Automation Products, the 670 series of relays support the subscription to 61859-2. So that's that from an IED perspective, though, those are the relays, though, that are supporting that information, that are supporting that implementation, though. So going back, though, to the logical node, to our logical node discussion, again, we're going from a model here in the left where we're defining, you know, where we're defining object types or registry types, whether they're binary or analog, meaning, you know, locations that can hold a 1 or a 0, or it can hold, you know, an actual, you know, binary value, to a memory, to an addressing structure where we're talking about functions and we're talking about pieces of information that are part of that function. So we see MMXU for metering, just how we see A. There's also V for voltages. There's also KW for real power and so on. From a protection perspective, just how we see OP for operation. We have STR for starter for pickup. For the position of the breaker, just how we have POS. We have data objects, though, for health. We have data objects, though, for whether the particular breaker is in local or remote. So there's a significant amount of pieces of information that are part of these functions, though. And again, the key is we're now not looking at an index or a registry that's part of analog values or binary values. We're looking at the functions and the data that's associated with those functions, though. And in turn, what that does is you essentially eliminate the need to have an understanding of, okay, for device A, analog input 55 has this meaning. And that connection, though, it's always part of some sort of documentation. In 61 and 50, there's not the need for that because the information, it's presented with the naming convention of these logical nodes or functions, though. So there's no need for a document, though. Everything is laid out based on this standard naming convention. When looking at the data model, though, again, we essentially, and looking at the logical node, we essentially have a physical device which serves as the outer boundary which serves as the outer boundary, though, or the physical casing, though, of an IED. Then we have what's called a logical device, which all it is, you can group logical nodes or functions within logical devices. And then inside logical devices, you have logical nodes. In this particular case, I have two examples. I have XCBR and I have MMXU. For XCBR, we have data object, though, that's called pulse for position. And then you have a value, okay, for the position, whether the breaker is open or closed. And then in this particular case for MMXU or my metering or my measurement logical node, I have a data object called A or amperes, and then there's data associated for phase A, phase B, and so on. Another thing that 61850 defines is that this data attributes, though, phase A, phase B, the status value, within 61850 7-1-2-3 and -4, there's definitions as to what is the format of this information in such a way that when we go and integrate or test the interoperability of devices, so an MMXU.A phase A, the data that that device reports, it's always going to have the same format. It's going to be a value in primary amps, okay? And these things are important when they're already defined, because what that means for us as a manufacturer is that we and other major vendors, though, of this type of equipment, though, we can design tools, okay, and we can have engineering processes, though, that essentially take this type of integration, and we now have an understanding that this is one thing that we really do not need to worry about. Also, when looking at the validation or the testing component, though, of the data model of devices, it makes it much more easier, though, and less open to interpretation, though, to perform a validation of the data model of a device. We can go in, we could see how a breaker is modeled, we could see what are the pieces of information within that particular logical node, and then we see the way or the format in which that information is being reported. And if everything checks off and it's per the standard, then a certificate can be issued to that particular device. Question came in. Are there any primary devices, breaker transformers, that can send goose messages on the market right now? You know, we really want to keep, you know, the webinar, though, for, you know, as you know, educational oriented, though. But the answer is, you know, there are indeed available in the market primary pieces of equipment that have electronic interfaces, though, that can, you know, that can subscribe to goose messages, though. Moreover, there are also available on the market electronic pieces of equipment or I/O boxes, though in our case we have a solution called the RTU 560, which it can actually be hardwired to a primary apparatus and then modeling 61850 that particular piece of equipment. So whether it's a breaker, transformer, and so on, it could be performed that. So even if you have a device that did not come from the factory with this electronics interface, there are options available to do that in the market from ABB. Real quick, this is just a quick list of different logical nodes. We have a logical nodes for protection-related functions, for control-related functions, measurement, automatic functions, instrument transformers, interfaces to switchgear, archiving, and so on. So there's really a significant amount of logical nodes / functions and equipment, though, that's modeled within this standard data model. So where am I going with all of this? Now, thanks to such representation, functions can be allocated to objects within the substation. So now, since now again I'm not talking about analog input 5 or binary input 7, there can now be an allocation or an addressing scheme for the information that takes into consideration the location of that particular piece of information. So instead of just having MMXU.A.phase A, actually from a gateway perspective, what I have is Bradley, name of the substation, then J1, the voltage level of that particular, where this particular bay is, Q08, the number of the bay within that voltage level within Bradley substation, A01, the IED that's associated with bay Q08 within voltage level J1 within Bradley, and then we can have the particular piece of information, which in this particular case is phase A current. Same thing for phase B current. Same thing for PTOC.OP, which is protection time over current. And same thing for our XCVR for our breaker. So the key here is now we have a comprehensive and thorough addressing convention, though, where we can now assign logical nodes to locations within the substation, though. So what this does is, from an integration perspective, though, we don't need, we don't really need, Excel spreadsheet or some sort of reference document, though, that somehow the integrator or the end user has to keep track of this DNP or this Modbus piece of information and its association with the application, and its location within the substation. It's all done within the addressing scheme of 61850. So just a graphic, though. This is GIS station, though, and here we could see how we have this allocation of functions, though. We have XCVR for our circuit breaker, and then here on the right, secondary functionality for our protection and control panel. We have protection time over current, we have protection distance, we have related to protection reclosing, we have control related interlocking, and we have controller relating switching, and this is, again, a distribution of the functionality based on logical nodes, where we are now assigning functions to the different pieces of equipment within the substation. And it's all done within this intuitive addressing scheme, which not only includes a definition of the function, but it also includes, there's also a tire and association with the location of that piece of information within the substation. Okay. Now, so we generate this naming convention. The next thing that this allows us to do is create a language, or SCL, or substation configuration language, where we can actually document all of this. So it's a language that, without having to use, again, I don't know, a Word document, Excel spreadsheet, we have a IEC 61850 defined language that allows us to document this. So what does it allow us to document? Well, it allows us to document the functions that are available within an IED. It allows us to document the one-line diagram of the substation. It allows us to document the association of those IEDs to locations or bays within the substation. And it also allows us to document the connection between IEDs. Some of the file formats, though, that are part of this SCL language, though, SSD, which is a specification of the substation specification description, ICD, IED capabilities description. This is what you could get from your IED manufacturer, your relay manufacturer, though, which would include a description of the functions that are available within that IED. A CID, it's a configure IED description. It's essentially an ICD plus any applicable configuration. You're sending goose messages, receiving goose messages, and so on. And then ultimately, though, the one that's very important, you have an SCD, which is a substation configuration description, which is essentially a file, okay, that contains the one-line diagram of the substation, the IEDs that are part of that substation, the association of those IEDs and their respective functions to the different bays and voltage levels within the substation, and then any type of connections that exist within IEDs. On top of that, we also include support, though, for an understanding of networks. You may have one, you may have multiple networks inside of a substation, though. at which point the STD file also allows for that type of documentation. So again, we document IDs and their connection to the application, functions and their connection to the application, communications network, connection between IDs, and then any type of applicable reporting mechanism. You could also see here that in this particular case, we have this substation, we have this voltage level, we have this particular bay. There are 5 relays associated with this bay, but then we're also documenting the clients, though, or the particular gateways, though, that are getting information out of these relays. And we also have the capability of documenting time servers. And you could see how these are all substation level functions rather than assigned to a particular bay, though. So it's pretty comprehensive platform, though, to not only document all that I've just described, but it's a tool to document the architecture of the system, though. And this is something that otherwise in a DNP or in a Modbus system, though, it will really come down to an Excel spreadsheet and drawings, though, to be able to represent all of this. Now, systems tool approach. Again, thanks to this common file format, though, the engineering, it's not just the file format, but also the standard naming convention. The engineering of the substation automation systems, though, in turn becomes it becomes simplified, though. And what this allows us to do is, since we have now a common file format and a common language, though, to document the capabilities of relays, though, and gateways, we can essentially, the engineering process, though, can be done in a centralized tool where the different vendors from the different vendors of IEDs can provide their ICD files or the IED capabilities descriptions, though. This information, it's the input to a systems tool. All the configuration related to the substation automation system is performed here. The output of this process, okay, is an SCD file or a substation configuration description, and then that file can in turn be used by the different relay-specific tools for it to be downloaded over to the relay. But essentially, this SCD file, if we compare it to, let's say Modbus or DNP, it's essentially the whole data map or points list of the whole substation with its association with not only the equipment, but also the layout of the substation, though. So again, our substation configuration description file, or our SCD file, includes files for each relay, which in turn have the list of logical nodes available for each relay. It includes a layout of the substation. Here we have 2 voltage levels, D1 and J1. We have 4 bays on each voltage level. And then we could see here how we also have a visual of how each IED or how each relay is associated with each particular bay. So now, thanks to all of this, though, let's talk about first protocol that we'll discuss as part of 61850. So client server. We now have this substation configuration language. We now have the standard naming convention, which makes integration and engineering much simpler. Client server really represents a way to exchange that information that's part of the data model from the IEDs over to a centralized location, gateway, HMI, RTU. And when we talk about lowering integration costs, we talk, it's because of this 3. Naming and understanding of the naming convention, okay? There's really not much manual typing. It's all a process of looking at the ICD file, looking at the available information inside of a particular device, and loading it onto our gateway so that it understands what is the information that it's going to receive from a particular device. Okay. We could look at here, for example, on this particular device, MMXU, our measurement function, and then we could see all the different data objects that are available, though. PHB, voltage phase A, voltage phase B, voltage phase C. From a protocol perspective, though, there are some additional features, though, that are worth mentioning. Discoverable mode. Essentially, IED supporting 61850 have the capability, or clients, which essentially it's a device that would like to read or be a client of an IED to obtain the information from this particular IED, can, without having any information other than its IP address, can connect over to this device and essentially get the information, all the information that it has available, or its data model. Okay, browsing this information. So again, without having to have a protocol implementation manual, I can go download from this particular IED its data model, and then browse through the data model and see what is the status of each one of the points that's part of that data model. Or, talking in 61850 terms, looking at the status of the different different data objects within a particular logical node. And then the last thing that's also worth mentioning, though, is the reporting structure. Information can be reported by a client browsing. Information can be reported cyclically, though, which is sort of similar to, static report, though, of information. It could be done via buffered report, where an IED can have several repositories of information. And by buffered, I mean this is information that's logged in a first in, first out fashion, though, and reported to a particular client. And we can have multiple client connections, though, and we can keep multiple buffers for each particular client, though. And then, last but not least, we have very similar mechanism, but unbuffered, and we could also still support multiple connections, though, to multiple clients. How are reports triggered, or how is the information pushed from an IED over to a gateway? Well, it could be, there's different ways of configuring it and different options. It could be done based on data change. When the data actually changed, let's say a breaker opens, a breaker closes, that in turn will cause a change inside xcbr.pos. Okay, change of the quality of that information, the update of the information within the IED, or again cyclic, where we just every so often the IED pushes the information over to the data concentrator. Now we get down to our final two protocols, though, that are utilized to digitize or replace copper wires, though, and that's goose messages, though, and sample measure values. Goose messages, again, used for rapid exchange of information between relays. You can exchange binary signals, okay, such as trips and pickup and any other type of binary signal that you can imagine that could be exchanged. And you could also exchange analog signals, though, or signals other than binary. For example, the position of the breaker, it's actually a 2-bit. It's a 2-bit data attribute, though, 00100111. You could also send the magnitude of a particular analog signal, though. But this is done in an asynchronous manner, though. So analog signals, they will not be, you cannot really use them, though, to operate metering or protection functions. And then the other one is sample measure values, or 61859-2, which is part of the process bus. So what is a goose message? Well, goose message is a generic object-oriented substation event. And again, this goes back to the UCA days, though, where something called GSSE was defined. It's essentially, same purpose, though, a way to exchange in an Ethernet network binary signals, though, from one IED to another IED. It's a fast and reliable distribution mechanism of information, though. Status, such as breaker position, trip, pickup, alarms, and analog values, counters, and so on. One of the questions that I often get is, what's the performance? Well, you have fast messages, though, which are based on 61A50-5, are type 1A for class P2 and P3, which these messages should be received within 3 milliseconds. When looking at the performance specifications, seems like we're having some technical difficulties with the audio.
Alejandro, I think we're okay. Go ahead. I think maybe it's a limited. I think it may be the one individual.
Okay, no problem. So you could still hear me. Okay, sounds good. So from a performance perspective, again, this is one of the questions that I received. What is the performance of a goose message? Well, there's different performance classes, though, defined within the standard. But for protection-related applications, though, the message should be received within 3 milliseconds. And what this means is we're looking at what the equivalent would be of the travel time of an output contact. So starting of the measurement time would be the point in which the condition becomes, changes state from 0 to 1 or from 1 to 0. Let's say a trip from the output of that function being de-energized to the output being energized. And then how much time does it take for that signal to be received by the device that's expecting that particular signal? So very similar to the sequence that would happen with a conventional output-input relationship, where the trip signal inside of the relay becomes a 1. That in turn drives an output contact. That output contact closes. There's a debounce time on the input of the relay that's connected to that particular output, and then the relay that's receiving that signal in turn says, okay, input 1, for example, is energized. Boom, it executes whatever logic it needs to execute. Debounce travel time of conventional output contacts, it's anywhere between a quarter of a cycle, which is 4.1667 milliseconds, to around half a cycle, which is about 8 milliseconds, though. Usual debounce time of protection relays, though, it's about, between 2 to 4 milliseconds, though. So when you look at that travel, the worst case scenario travel time plus debounce time, you're looking at about, 10 milliseconds, though, that it would take for conventional output contact to become a 1 and be recognized as a 1 on the receiving relay. On 61A50, that exchange happens within 3 milliseconds, and the gain in performance is thanks to the fact that these are communication messages that are properly framed. There's checksums, there's integrity checks, so you really do not have any type of noise concerns at that point. Information, if the packet is properly structured, though, then it's being trusted, though, for that change. So there's no need to further delay the sequence of events that a particular goose message generates. So goose messages, though, how are they sent? Well, goose messages go out in two fashions. So one is whenever any of what's called data attributes that are part of the data set that the goose message is sending changes state. So goose messages are changed based on a change event. And then the second way that goose messages are sent is there's a cyclic or a heartbeat type function where based on a parameter of a configuration parameter of the goose message, so we will send a cyclic goose message just to indicate that the connection between the device that's sending the message and the device that's expecting that message, it's an integrity check to make sure that that connection it's still good. Okay, so but for whatever reason the device that's sending the message fails, if the network connection fails, the device that's expecting to receive that message after that period of time, okay, that's predetermined, if it does not receive an update message, then it deems the connection as gone bad, and that can in turn be used to drive similar, an internal relay failure alarm or some sort of alarm to indicate that that the connection is no longer good. And this is where, when we talk about disassociations being self-monitored, this is what we mean, and this is the mechanism that's used to monitor them. So I have a question here. Does the station bus need to be an isolated network? What happens to performance if there is other Ethernet traffic on the network? Very good question. So by station bus, we're talking about goose messages and client server. I'm not sure what's meant by other network traffic, though. I mean, this is the Ethernet network is it's really supposed to be within the substation. So if there's other pieces of equipment within the substation that are generating Ethernet traffic, though, for other protocols, though, there shouldn't be that should not be a problem. File transfer and so on, that should not be an issue. In the case of goose messages that are for protection-related applications, it is important to take into consideration and utilize what's called VLANs or virtual LANs and assign proper priorities to that traffic in such a way that the switches that are used to form the Ethernet network will be smart enough to assign proper bandwidth to those communication messages that are time critical. Definitely, if you're doing file transfers in that particular network, that is going to put a load. Okay. However, if using virtual LANs and using proper priorities and assigning priorities properly, the switches will assign the needed bandwidth to those time-critical applications. So there will not be an impact on performance on the goose message application. There may be an impact on your file transfer, but if it's not something that's time-critical, it will be something that will not be noticeable. Okay. Now, if we look at some of the parameters that are used, if we look at what's sent or what's inside a goose message, though, well, inside a goose message, what we actually send, it's a data set. And what a data set is, it's essentially a shopping bag or repository of pieces of information inside of the relay. So in this particular case, I have a data set called protect, and I'm sending the general or the three-phase signal for my instantaneous or recurrent protection function, and then I'm also sending the phase segregated ones for phase A, B, and C. And then what are some of the attributes that need to be, or what are some of the configuration parameters, though, that need to be set on a goose message? Well, as I said, you have a VLAN ID that can be assigned, priority, okay, that can be assigned. You have a minimum time, which is a filtering time, and then you have a maximum time, which is, and this, both min time and max time being in milliseconds. This max time is the maximum amount of time that devices that are expecting the goose message to arrive would wait for a new update to come through as part of this, cyclic check. Okay. When looking at the engineering process, essentially you configure your goose message, you configure what's going to be delivered as part of that goose message, and then based on the system tool that you're utilizing, though, it's just a matter of checkboxing, or there's different tools from different manufacturers have different mechanisms, but essentially what you have to do is make an association between the devices that you want subscribe to that particular message and the message itself. So when looking at goose message, what are some of the applications that have been deployed? Well, pretty much anything that requires exchange of information within relays that's currently done today via hardwire connections. It's a candidate for it to be replaced with the goose message. So some examples are breaker fail scheme, initiation of a station digital fault recorder, alarm annunciator, transfer schemes, reclosing multi-breaker arrangements where you may have multiple reclosing functions and you may have a lead follower type scheme, and there may be hold or block type signals though between these devices. Also in teleprotection though, the signals that go from the relays to the teleprotection unit within the substation, that is something that's hardwired today. It's something that could be performed with goose messages. Now, let's dive into the process bus, okay? And when looking at our process bus, what we have here is a series of 6 panels, though. And each panel, it's kind of hard to see in the presentation depending on the size of your screen. But essentially, you would see that on the left, we have a scheme where we have these relay panels, okay? We have breakers, we have current transformers, we have voltage transformers, and then there's hard wiring between those. We have hard wiring though between breakers, between current transformers, and between voltage transformers and the bay or the panel. When we look at the 61850 process bus, what we have is we have the same relay panels, but instead of having hard wiring between the current transformers and voltage transformers and the relays, what you have is inside the breaker cabinet or inside the breaker cubicle, you're going to have an electronic piece of equipment known as the MU or the merging unit. And the merging unit, it's going to have hard wiring between CTs and PTs, okay? So on one side, you have terminal strip where conventional CTs and PTs or non-conventional CTs and PTs are connected to the merging unit. And then on the other side, or the output of the merging unit, it's an Ethernet optical interface that connects over to an Ethernet network that in turn publishes or sends the digitized current and voltage signals. The idea behind this concept is twofold. Number one, you are providing total isolation between the control house and the primary equipment. Okay, so things such as open CT circuits, though, and issues with the isolation of VTs, though, it's something that's addressed, and that is an issue inside the breaker cabinet, but it's not an issue inside the control house, since the signals are coming in the form of digital Ethernet packets via the communications network. That's one of the things. So safety is one of the elements that 9-2 addresses. The second element that 9-2 addresses, though, is the flexibility, though, or the ability of sharing analog information among more devices. So right now, depending on the practices that are used by a particular utility, though, you will need 1 CT per IED. You may be able to connect 2 IEDs to a particular CT, but ultimately, though, you will need several CTs, though, from a particular breaker bushing, though, to serve different applications, though. You may have 1 CT that's used for your bus differential, and then 1 CT that's used for some other application, metering perhaps, though. With the concept of the merging unit, though, you can have a single sensor or a single CT monitoring your current signal, or a single voltage sensor monitoring the voltage at a particular location within the substation. Once the signal is digitized by the merging unit, that is published onto the network, and whatever IED wants to subscribe to that particular information, as long as it has the capability to do so, it can. So it really allows to it really allows us to share more analog information, though, in an easier way. Okay. I'll address those questions like towards the end, since we're running a little bit out of time. Okay. So when looking again, when I refer to as publishing though, the merging unit, it's gonna again sample the current and voltage signals. It's gonna publish it though in the form of Ethernet packages though, and every device that's connected to the network, it's gonna receive the information, and it is really up to every single device to decide whether they want to use that information or not. And there's obviously a configuration process though that needs to happen for, let's say, line distance relay. You need to define which are the sample measure value data streams to which that particular protection function will subscribe to run its protection algorithm though. Now, since this merging unit, or you could have a relay that may be receiving this data stream from more than one merging unit, the synchronization of these samples becomes important. If you have one merging unit that has the current signals and then another merging unit that has the voltage signals, and you're receiving that, or in the case of differential protection where you have, two or more sets of current signals that are being compared, these current signals and voltage signals, quite frankly, everything needs to be referenced to time. And this is the part where, in the case of the original 61859-2, there was not a particular implementation rule as to how that was going to be. And that's where the UCA International Users Group came out with the implementation guideline, where, again, we define sampling rates, we define structure of the data stream, we define acceptable synchronization sources for time, and so on. Okay? So here are some examples. In the case of time synchronization, pulse per second, or PPS, it's what we're looking at as a synchronization source. Content of data set. In 61859-2, it was a configurable attribute. In 9-2LE, it is defined that one data set, or sometimes it's also referred as a data stream, you're going to include three-phase currents, three-phase voltages, plus the neutral current and the neutral voltage. So on a particular data set or data stream, you're going to receive 8 analog signals. Okay? And then the other part that was left to interpretation or left to implementation was the sampling rate. And 61859-2LE, or the implementation guideline, defines that you should have 80 samples per cycle for protection functions and 256 samples per cycle for power quality monitoring type functions. And this slide just refers to the synchronization, okay? It is important that each relay or each IED that's going to be subscribed to these data streams, though, that have the capability of aligning these signals, though. And the way those signals are aligned is based on a definite time reference, though, which, as defined by 61859-2LE implementation guidelines, it's based on PPS, pulse per second. Some of the benefits, though, as I just described, though, you're really looking, though, at safety, though, since you now have total isolation between CT and VT circuits, though, and the control house. Reduced life cycle costs. There's permanent real-time system supervision, though, to verify the integrity of current and voltage signals, though. Reduced amount of copper cabling, though, and trenching, though, from the switchyard over to the control house. And future-proof by having an interoperable design, which, again, this exchange of information is not based on proprietary protocols, but it's based on IEC 61850, which is an open standard. One other thing that's very interesting about this technology, though, is the impact on testing and commissioning, though, and how now, from a testing and simulation perspective, though, there are 9-2 LE test sets and simulators, though, that will allow us to simulate power system conditions and see how the protection elements operate, just like they would if we were doing conventional secondary injection with a double, mega, or Omicron tested, though. What's interesting about this is now, from a test switch perspective, though, you already have an isolation, though, so that's another source of panel space saving, though, that comes from, though. But obviously, since now you have a whole digital environment, though, we do see, though, that from a testing perspective, though, a lot more scenarios, though, that can be utilized, though, to validate the protection and control schemes. Okay. Another thing worth mentioning, though, is that since this samples of this data streams of information, though, are available, you can now essentially have a centralized location to view all this analog, both current and voltage information, similar to an oscilloscope, though. And there are tools available now that allow for such visualization, though. So that's something that's also pretty important, though, to take into consideration. And also, since now all these pieces of equipment are digital, they can be monitored. From a maintenance perspective, though, you're looking at a system, though, that, if it fails, it will let you know that it has failed, or it will let you know that it has malfunction, though. Just really presenting opportunities, though, for savings in preventive maintenance. One last topic, though, that we'll touch on this presentation, though, is something that's coming up with IEC 6150 edition 2, and that is the need for redundancy in the network, though, and also the reliability of the network, though. When looking at the network itself, or the Ethernet network, it needs to be taken into consideration, though, that the same standards under which IEDs that relays need to comply to, your Ethernet switches and network infrastructure need to comply to as well. And part of IEC 6150-4, there are standards for dielectric surge withstand capability and RFI for which equipment needs to comply to. So you'll start seeing RuggedCom, GarrettCom, and other switch manufacturers, though, stating that they're 6150 compliant. And actually, what that means is that they comply to all type test information that's defined in IEC 6150-4 in regards to dielectric surge withstand capability, radio frequency interference, and so on. But it's also important to take into consideration, though, the redundancy, though, of the network. And there's actually two technologies, though. You have HSR and PRP, and we're from PRP perspective, though. PRP stands for Parallel Redundancy Protocol, though. And the idea of PRP, though, is to have two simultaneous networks running in parallel, though, in such a way that traffic is replicated. And if you have a point of failure on one of the networks, there would be no impact on the delivery of the information from point A to point B, since the parallel path or the parallel network should have not been, affected by that particular event. So the idea, again, is you essentially have two parallel paths to deliver the information, though, from point A to point B, and that is, in a nutshell, though, what it is. So just to wrap up, though, really it's been market requirements, though, that have been driving IEC 6150 as a standard, though. Cost reduction in design, construction, and better way to operate and integrate the system, though. Improved power system reliability and safety, though. Goose messages, though, and sample measure values. Their digital nature, though, allows us to monitor their integrity, though, their connection, as we discussed, sample measure values, providing an isolation barrier between instrument transformers and the control house. Safeguarding of investments, this being a global open standard, and one big one though is the interoperability between IEDs from different vendors though. And this is something where 61850 being an open protocol, but also having part 10, which includes procedures though for the validation and the verification of the data models of devices though. It really adds another layer, an extra layer of security though, to ensure that this interoperability does exist. Now, I'm going to go ahead and answer some questions though that we have here pending on the queue. So, one of them is 61850 communication common between substations that are geographically remote? As part of edition 2 of the standard, this is something that has been defined in the sending and receiving of signals from 2 substations that are geographically remote, or 3 substations, or 4 substations that are geographically remote for transfer tripping capability, for transfer tripping and for teleprotection type signals. It's actually something that is common and is indeed done utilizing goose messages over goose. Okay. Another question that I have here, does it mean the traditional RTU devices will lose its market with IEC 61850 applications? I think that there's definitely been a significant amount of depending on the best of the practices though of the particular customer and user though. There's been a migration from RTU panels, okay, from that initial architecture though, to utilizing the data that's available within the relays to report it back to the SCADA or the control center. So there's definitely been a loss of market from that particular perspective though. Now, 61850, I don't really think that adds, more to that loss. However, I do see RTUs with the capability to model pieces of equipment that do not have electronic interfaces, such as breakers, transformers, load tap changers, though, becoming in higher demand if they're able to essentially model that particular piece of equipment in 61850. So, for instance, if you have a conventional breaker, you can have an RTU or an I/O box that can have, from one side, the hard wiring to A and B contacts, closed coil, trip coil, and status signals. Then on the other side, you could have an Ethernet interface that will, in turn, report the status of those signals, as well as having the capability of receiving goose messages, though, for trip signals or closed signals. So that is an application where we see, smaller RTUs becoming becoming a part of this picture, though. I have another question here. Please discuss the impact of the time source becoming unavailable. For instance, will protection stop working? Thank you. That's a very good question, though. So similar to this, the way this was thought of from a from perspective, though, it's really similar to a line differential relay, though. If applied in a SONET network, though, where you can have asynchronous, where you can have unsymmetrical delays, though, on your channels, though, as part of the Ethernet packet that contains the sample measure value data stream, there are flagged bits for synchronization, though. And if the merging unit loses its source of synchronization, it will set this bit, and then in turn, the particular devices that are associated with that data stream will know that the synchronization has been lost. Okay. For a short period of time, just like line differential, though, they will continue to be, they will continue to have the capability of operating, because the drifting time of such clocks, of the clock of devices these days, it's quite finite, though. But at some point, if the synchronization does not come back, though, that definitely will, at least the devices that are subscribed to that particular datagram, though, will not be able to make use of that information, though. And let's see, I have another question here. Does the use of goose messages and a station bus introduce any additional cyber vulnerabilities under the SIP standards? That's a very, very good question, though. From a NERC SIP perspective, though, you're really addressing routable protocols, though, and goose messages, though, are not a routable protocol. So if you look at, from the regulations perspective, though, you're really looking at, protocols that have the capability of going over different networks, though, that are impacted, though, by the NERC SIP regulations, though. Also, your NERC SIP regulations, though, become a concern from a station bus perspective, though, if there's a connection to the outside world from that substation, though. And really, the considerations are not different. The security concerns are none different than with any other communication protocol, such as Modbus and DNP, though. 61850 does provide, within its framework, though, enhanced layers, though, and further layers of security, though, to validate who's sending particular commands and so on. But to answer your question directly, goose messages are are part of a non-routable protocol, and a goose message, though, lies on layer 2 of the OSI model, though, so it technically cannot go from one IP network onto another. One question that I have here is the 61850 standard addresses asset management of electrical equipment. That's a very good question. What 61850 addresses, it really makes the information available, and it provides the data model, though, that's standard enough where the manufacturers can make such information available, though. But 61850 at no point really defines such type of functionality as to algorithms, though, to estimate the loss of life of a transformer. What 61850 would do for you, it will make the information that you need to run that algorithm available. Good question. I have a question here that says, how does goose go from one remote location to another transfer trip without being part of a routable protocol? That's an excellent question. The applications where we've seen this applied, you actually have a direct fiber network from one substation onto another substation. Okay, it could also be packet as part of the SONET, as part of SONET, though. If a SONET communication ring exists within substations, though, but goose itself, though, it's a layer 2 protocol, though, so it's not dependent on IP addresses. And for protection testing purposes, we're just going through some of your questions, though, and we're actually we ran out of time about 25 minutes ago, but the questions are pretty good, though. So I'm going to go ahead and answer one last one, and then we'll wrap it up. Let's see. With virtual wiring, how to isolate a relay for protection and testing purposes? That's an excellent question, though. And again, this is a lot of this. They really get into details, so that's really impossible to cover in just an hour and a half webinar, though. But both sample measure values as well as goose messages have a flag bit for testing, in which you can grab a particular relay and set it in test mode in such a way that you can test the relay, and if that particular relay is generating changes of states or it's broadcasting goose messages that do indicate the activation of a particular protection function, those changes of state will in turn be ignored by any other relay that's subscribed to that piece of information, since they recognize that that device is in test mode. So in the case of, let's say, a breaker fail scheme where one device is being tested and you're applying current to it, and that in turn is generating a goose message that's used by another device to start the breaker fail, pick a timer. If you set that relay on test mode, the device that has the breaker fail timer will recognize that that device is in test mode, thus it will disregard that particular message, thus avoiding the actual operation of the breaker fail scheme during a testing scenario, though. So there are mechanisms that were thought of to ensure the flexibility of both operation and as well as testing. But that really does it for today. This webinar was brought to you by Reliant product family, next generation of protection and control IDs from ABB. Reliant, the perfect choice for every application, widest range of products for power systems, protection, control, measurement, and supervision, interoperable and future-proof solutions designed to implement the core values of the IEC 61850 standard. ABB's leading-edge technology, global application knowledge, and experienced support network ensures complete confidence that your system performs reliably in any situation. And Reliant provides protection and control solutions from high voltage and extra high voltage protection relays, though, all the way down to simple overcurrent microprocessor relays and everything in between. All devices can be set utilizing the same software, thus having same similar sets of settings, same user interface across a whole array of applications. And again, this is it for today. I would really like to thank you for your participation and the opportunity for me to speak to you. And shortly, you will receive a link to an archive of this presentation. And you can visit us at www.abb.com/Reliant. Thank you very much.